Hello and welcome back to Odds. In this video, we'll be going over something a bit different from my usual videos, which is deriving the big five kinematic formulas. And how we're going to do that is we're first going to go over the intuitive ones, and then we're going to go over the derived ones. So we're going to start with, this isn't a part of the big five by itself, but it's still important for this video. Hf is equal to Hsi plus Vt. Okay? The position time equation, which is pretty intuitive, right? Hf is your H's final position. H's initial is your H's initial position. Velocity is your change in H's over change in time. And if you multiply that by time, you should get change in H's. Hsi plus delta H's is just Hf. And it's also intuitive for one more reason, right? Because velocity is just equal to delta H over delta T. And for example, if you started at 2 meters and then you started at 2 miles and then you went at 30 miles per hour for 2 hours, you know that you would have gone 60 miles, right? And then this would be 62 miles, would be your total distance or position. And why is that? Because it's intuitive to you. But when you analyze it, it's really just you're multiplying these two, canceling out these units, and then getting distance. And then adding that to Hsi to get your final position. I also went over this in one of my other videos if you want to look at that. Because of the same reason, we know that Vf is equal to Vi plus At. And this is one of the big five. So why is Vf equal to Vi plus At? Well, you know that acceleration is a change in time, change in velocity over change in time, right? So if you started at 0, or whatever your initial is, meter per second, and you accelerated at 10 meter per second squared for 3 seconds, you know that your velocity would now be 30 meter per second. But where did you get that from? Your brain might be going ahead of you and you might be doing it by reflex. But the thing is, you cancel out these seconds, you get 1 second. 10 meter per second times 3 is just 30 meter per second. And that's your final velocity. Your acceleration is how fast your velocity changes, right? So it makes sense that your acceleration is the slope of this graph, at. Vi is like the mx plus b here. And then at is your acceleration, which is the slope of the velocity graph, times your x value. So multiple ways of looking at it, but it's all just intuitive. Now, we're going to go over the other formulas in a bit, but there's one more intuitive formula, which is V average is equal to Vi plus Vf over 2. And this is only for constant acceleration. What do I mean by that? Well, think about it, right? Vi plus Vf over 2. If you had a line, then you can pick two accelerations or velocities, and you can say that the average is between those velocities, right? But you can't say that when your graph looks like this, right? Because parabolas don't have averages. Don't have a linear rate of change, so you can't take an average here. You might get an average value, but that wouldn't be the actual average value. Because the thing is, parabolas need you need a linear rate of change for an average to be right. You can still get an average, but not a right average, right? So this wouldn't be right. And this is just a regular average formula, so that's how we got that. Okay. And then we're going to start deriving now. So instead of V here, Hf is equal to Hsi plus Vt. Think about how we can replace that V so we can get a more average V, right? Because what if the position graph here looks like this, or something close to that? I mean, it's not linear, of course, because the graph here is just linear. And this graph, the quadratic I drew, wasn't linear, but forget about that. this would be velocity average, right? Because what average are you talking about? Or what velocity are you talking about? If your velocity keeps changing, then you know your velocity average has to be the one you use, right? So that's why you're going to use velocity average times t. And what can we sub in velocity average for? This thing. So HF is equal to HI plus VI plus VF over 2 times t. Pretty simple, right? Sometimes you get more velocities, right? And then if you want to just take the average of them, you can just do it like this. And then you can use the velocity average in your position time equation. Now, we're going to simplify this equation here. So I'm going to go up here because I'm going to use this for my work now. As I simplify it. If you subtract HI from both sides, on this side we get HF minus HI. And we know that's what value? That's delta H, right? That's displacement. So delta H is equal to VI plus VF over 2 times t. And then instead of VF, what value is VF equal to? Well, if you look here, VF is equal to VI plus AT, right? So we can say delta H is equal to VI plus, we're just subbing in this value, VI plus AT, because velocity final is over here. Velocity initial plus AT. And that over, all of that over 2 times t. So if you simplify this, we can add both the two V initials. You get 2V initial over 2 plus AT over 2 times t. Delta H is equal to velocity initial plus AT over 2 times t, right? Over here, the velocity initial just cancel out the 2's. And then when you multiply here, delta H is equal to velocity initial times t plus 1/2 AT squared. Now this is one way of writing the equation. You can also write it like this, right? HF is equal to HI plus VIT plus 1/2 AT squared. Either of these mean the same thing. If you just subtract HI, you can get delta H, right? So they're pretty much the same. And even if I kept that HI at the start, you'd still end up with the same answer. So it doesn't really matter here. And then let me go to, now I'm going to scroll up so you won't be able to see the others. So I have more space here. And then I'm going to work with my other equations. My final equation, I know I'm not going to have t. So let me look at this equation here. Let me drag this one into my derivation playground and sub in t for something. Well, I know VF is equal to VI plus AT. So I know VF minus VI over A is equal to t, right? So I can just sub that in for t. So HF is equal to HI plus VI plus VF over 2 times VF. So now let me erase this. But you get the idea, right, where I got that from. Times VF minus VI over A. So if I subtract the HI from both sides here to get rid of this, I get 2 delta H. Oops, just delta H, no 2. But ahead of myself there. And get VI plus VF over 2 times VF minus VI over acceleration. Let's say I want to get rid of the denominator, so I can just multiply them both out, right? So 2A delta H is equal to the difference of squares between VI and VF minus VI. So I know using difference of squares, this is going to give me 2A delta H is equal to VF squared minus VI squared. And then if I just add this, vf squared is equal to vi squared plus 2a delta x. And there you go. That's your velocity displacement equation, which doesn't use time. These big five equations have a big hold across kinematics, okay? And using these equations, you can solve multiple problems, because even if one variable is missing, there are other equations to do the job of collecting that variable, or or they have equations that are missing that variable. So then you can use those because you don't have that variable. Multiple different things you can do there. So to review, vf squared is equal to vi squared plus 2a delta x. Then delta x is equal to vit plus 1/2 at squared, or xf is equal to xi plus vit plus 1/2 at squared. Then we have xf is equal to xi plus vi plus vf over 2 times t. V average is equal to vi plus vf over 2. And velocity final is equal to vi plus at. And there you go. That's your big five derived.